As I told you last time, what I'm going to do today is just tell you a bit more of like the rules of how to do the double integrals in Cartesian. And then depending on how much time we have left, we'll move to polar coordinates, which is the last topic for the exam. So let me write like a couple of rules of how like the integration is supposed to go. So if you remember from Monday, for all these problems about double integrals, really setting up the bounds is kind of like the crucial part because once you have like the correct bounds, doing like the integrals is not that different from doing like the regular integrals from Calc 1. You just have to remember to keep one of the variables constant. So how to find the bounds for a double integral? So this. And then I'll do a few examples to show you how this looks. So the idea, say you have like a region R on the plane. Okay, I'm drawing it a bit amorphous. Like usually the regions we'll work with are kind of like triangles, lines, things determined by parabolas, discs, half discs, like, and they would be more familiar. But here I'm just drawing like some random region on the plane. So as I was saying like last time, the idea to think about the double integral is that there's like the graph of the function that lives on top of the region in a way, and then you're trying to find like the volume between that graph and the region, and then it's kind of like the piece of bread, right? Like there are different ways to chop it off, and then like if you cut it in kind of horizontally versus vertically, that still computes the same volume. It's just that depending on how you cut it, like then one of the variables is held constant. So I think these were like the colors that I used last time, but um, say if you cut the region like using like vertical cuts, then what happens here, like the y variable is the one that's changing. So what that means is that you integrate first with respect to y. So that is usually called the order of integration dy dx. So let me put it like this. And the reason why it's called like that is that when you see the integral, the double integral, you integrate first with respect to y, and then with respect to x. So when you write this like from like in the usual way from left to right, you just it reads dy dx. So that's why that's called like that. And then so the idea for like setting up the bounds is that when you break that region vertically, it's better to think about it more in terms of an animation. So you have all these arrows moving upwards, like from south to north. And so the lower bound, again, because this is like an integral for y, the bounds have to be like y equals something, y equals something. Okay. So the lower bound is where, it is the equation where the arrows enter the region R. So this will be the equation where the arrows enter the region. Okay, and because this is an equation for y, it is allowed to depend on x. So these bounds can be a function, like the rule will be like the bounds can be a function of the remaining variable. So in this case, like the one that you're going to deal with first is y. So that the remaining variable is x. So the bounds are allowed to depend on x in general. And then you imagine like the arrows moving up, 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 and then they will exit the region through some curve. And so the top bound will be the equation of like the curve that the arrows exit the region are. So this is going to be the equation where the arrows exit are. And again, that is allowed to depend on x. So both bounds on the inside, like or like the first one that you do, can be functions of x. Okay. Oh, and then the once you have that, which usually is kind of like the most important thing to figure out, like the inner bounds, if you want to call them that. Once you have that, the like outer bounds, the last integration, then has to be bounds for x, and then that's just you know, that is between which values of x do you have to move like these vertical arrows around. So essentially, these can only be numbers, and the numbers that they correspond to is kind of like the minimum value of x in the region. So there's like a, I don't know, maybe there's like a minimum value of x here, right? Well, actually, the minimum value of x is probably like somewhere in here. So there's a minimum value of x in the region, and then there's a max value of the x coordinate in the region. And that is between that, those are the values that you have to move the arrows around. So the bounds for x go from x min to x max. Okay. Is that making sense so far? Okay, and then the point is that and you'll see with these examples, like you, in principle, theoretically, you could always do the integral in this way. Sometimes it is easier to do it in the opposite way, where like, you know, you break the region horizontally, and other times it's kind of like, you know, about the same level of difficulty. So it does depend a lot on the specifics of the problem, but the other way to, you know, to break this region apart is like using these horizontal cuts, which then looks like this. And that's called the order dxdy. And the idea here is that along each horizontal arrow, the x variable changes first, or like is the one that's changing, like y is fixed. So that means that you're integrating with respect to x. So the way the integral looks, you like integrate first with respect to x. And so because the integral is first for x, the bounds need to read x equals something, x equals something. So now the thing is that the arrows are moving horizontally. So the idea is like the arrows always move in the direction of the increase where the variable is increasing. So the x variable increases from left to right, or like west to east. So that's why I'm drawing the arrows this way. So the lower bound is kind of like the region, like the equation that the arrows hit first. So it works similarly as like the previous case. So this is where the equation where arrows enter R. The difference now is that because this is an equation for x, it can be given in terms of y. So that's where like you can reverse the roles. So so this equation is allowed to depend on y. I don't know why. Okay, and likewise, the arrows move through the region. They keep moving. They keep moving. until they exit somewhere in here, and so the the top bound will be the equation where the arrows exit the region. Equation where arrows exit are. And again, it can depend on why. It doesn't have to, but it is allowed to depend on why. So it can depend on why. So that's like the setup for the inner bounds look in this case. And again, it's called the active y because if you read the integral from left to right, then you see the active y. Okay, so actually that's another way to refer to this like different orders of integration. And then for the y bounds is similar here, like you want to, since now this is the last thing you do, you like the bounds are for y, so you have to put y equals something, y equals something. And the idea, as just like the previous case, is that what you do is kind of find the lowest as smallest and largest values of y in this region. So I don't know, maybe the lowest value of y is somewhere in here, so let's call it y min, and the largest value of y is like somewhere in here, so it's kind of y max. And those are like the two values that you have to move like the horizontal arrows between. So you think about the arrows as something that's sweeping out the region. So you can start them at the minimum value and then increase them until you hit the top value. And so that's why these bounds go from y min to y max. Okay, so let me do a bunch of examples that I show you where I'm going to show you how to set up the bounds. So I'm not going to like last time on Monday, I kind of did it for like specific functions, like the integration. Here, like as I'm saying, like really like 3/4 of the problem is just about finding the bounds. So I'll just call the function f of x comma y because we don't really care too much about what this function is. Maybe I'll write this explicitly, because it's like a useful thing to mention. To determine the bounds, the function plays no role whatsoever. So the determination of the bounds is entirely in terms of like the region itself. Like the function could be whatever you want, and that doesn't have any effect on what the bounds are supposed to be. So to determine the bound, to find the bounds, the function plays no role basically. So it really only depends on the region of integration R. So which is why the pictures I will do are just for the region and not the graph of the function, because the graph of the function plays no role whatsoever in the bounds. Okay, so for the next few examples that I'll do, I just will call the function f of x comma y just to have something inside the integral. And then, yeah, in specific problems, and you would be given different formulas for f. But for now, there is just about like finding the bounds. In fact, like, if you have seen practice exams, like you'll see that sometimes there's like just like a problem where you just write the bounds and there's no integration that you're being asked to do. So because like sometimes like, yeah, like the more interesting part in this course is kind of like just to determine the bounds. So um, okay, so let's start like with we'll try to kind of increase a little bit the difficulty of these examples. So let's start with something somewhat easy. So Where are we get in the first quadrant? Okay, so I'm trying to write it in a way to how you would see it like as an exam problem. So as I mentioned last time, like at least you are expected to know how to draw basic regions by basic things that involve parabolas, lines, like maybe like a root of x, equation of a circle, like a triangles. That's kind of like the types of things like nothing crazy, but like so usually like for something of this sort, like you wouldn't be given like the picture of the region. So it's kind of like useful to just like be acquainted with that. So the first step, like, and really in all of these problems, it is better just to always have the picture, uh, even if you are not asked explicitly to sketch it, because just going with the algebra is possible. Like, you could just look at the equations to do it in your head, but it really just so much better to have like a picture in every single problem. So, um, well, it's going to be in the first quadrant, but I'll still try to draw kind of like the graph of the functions or like the equations. So let's start with the easier one, which is like the parabola. So that's a parabola, looks like this. And then the other one, which is the square root of x. Not sure how much you remember from the square root of x. There's not too much that you need to remember, except that you draw like thinking like the square root is only defined for non-negative numbers, like it consists at 0 is 0, and then you draw something like this, and then this will be this. In fact, let me try to do it a bit bigger so that like um now it looks better here. So the region R is the region in the first quadrant determined by these two curves. So it essentially refers to this. So here. Okay, and then essentially is all in these pictures it's also useful to find like you will need it at some point, find where the curves intersect, right? So clearly they kind of meet at the origin. That one is easy to see. And and then they also meet at this point, and then you have to find out the point. Like that it happens when x squared equals root of x, which can only occur when x equals 1, if you think about it, because you can like square both sides of the equation and that gives you x to the 4 equals x. And that again like, can only happen when x equals 1. So there are a couple of ways to see it, but like the intersection happen for x equals 0 and x equals 1. And when x equals 1, the corresponding y value is 1 as well. So kind of like the region looks something like that, like what I'm showing you here. And another thing that can be confusing is like, how do I know that like, root of x is on top of the parabola here? And remember, like when you have numbers between 0 and 1, like the square of the number is smaller than the root of x, which is kind of a bit confusing. But like, if you think about it, like for example, square root of a quarter, 1/4 is 1/2, but 1/4 square is 1/16. So squaring a number between 0 and 1 makes it smaller than taking the square root. And that flips once x is bigger than one, which is what you see in the picture, right? So once the number is larger than one, squaring the number gives you something bigger than taking its root, if that makes sense. Is that okay? Okay. Okay, and so now like the setup, once you have that, like once you have like a good picture, like really that does help a lot in the problem. So let me do it in both ways. Like again, we don't care too much about doing the integration because we're just learning more how to find like the bounds. So for like the first option, like you have to use vertical arrows. Okay, which look like this. So this is what I'm calling the order dy dx. And as I was saying, like, usually people don't write like the parentheses. Um, you kind of get used to not writing them out explicitly, so I won't put them in here, but it still means that you're integrating first with respect to y. So you have to put bounds for y, and then whatever you get afterwards, after you do this integral, you will integrate with respect to x, right? Um, So again, like, in terms of like the animation, it's just like imagine like the arrows, incoming arrows, vertical arrows moving towards the region. So you see, like they all have to pass through first, like the blue curve, right? The blue curve is a parabola, so that means that the lower bound should just be y equals x squared. And then the arrows move up, 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 and they all have to exit through the orange curve. The orange curve is the square root of x. So that would be the top bound. Is that making sense? And usually the inner bounds are kind of like the more complicated ones. Once you have those taken care of, then the x bounds are just like, as I was saying, like smallest and largest value of x in this region, which we already determined earlier when we found the intersection points. That's also another reason why it's useful to find the intersection first. So you can say that it goes from 0 to 1. Okay. Is that okay? Making sense? Questions? Yeah.
Obviously here it's obvious on the graph, but, for, I guess, maybe more complicated equations, how should we like prove? Or would we need to prove?
You don't need to prove anything. Yeah, no, as long as like,
As long as you pick the right.
right, like it's kind of like the idea is kind of extracting the data from the picture. So as long as you put something that's correct, you're good to go. Like you don't have to justify it, if that makes sense. Like kind of like having drawn the picture, like and putting like an arrow here, in a sense, tells me that you know what was going on. You know what I mean? Right. In fact, like it's again, like, strictly speaking, like if you just are asked to find the bounds, like, or write the bounds, like you could just put this without the picture, right? Like obviously it does help more like to have the picture, but unless you're asked to sketch it, like you're good, like that's fine. So, but yeah, like that's kind of like the pro and con of this type of problems, that is really just kind of like either you see it or you don't see it, if you know what I mean. Like there's not much to justify, kind of it will become apparent after you have done it, done a few examples, but there's not much to manipulate algebraically to say what's going on. And let's flip the order again just to practice this. So if you flip the order of integration, that means you want to use horizontal arrows. And let's see. Okay, so here again, it means you're going to integrate first with respect to x. So you are using the horizontal arrows which move from left to right. So you have all these incoming arrows, and now you see that the arrows, what they would go through first in this region is now the orange curve, right? So they pass first through the orange curve, and then you say, okay, what's the equation of the orange curve? It was y equals root of x. The problem with how it's written now is that it is given in terms of y. You have to flip the roles around, so you have to solve for x in the equation. Once you do that, everything else is fine. So you have to square both, you can square both sides, say that root y squared equals x, and that is now the equation for x that you want to put as the lower bound here. Is that making sense? Uh, and then the top bound, like the arrows move, and then they exit through the parabola. And then again, the issue with the parabola equation is that it's in terms of y, so you solve for x here, so you can take the root of y equals x. And that is the bound, the top bound now. Is that okay? And so, like, that's also why it's useful to use the colors, because if you look at the colors, like compared like the orders, kind of like the orange became, when here was at the top, now becomes the bottom, and then the blue, which was at the bottom, because goes to the top once you reverse the order. So like they're really, it is, you cannot just like read one of the orders and kind of like do like a weird trick, algebraic trick, where you just like move them around. Like you do have to think a bit about what's the effect on the picture itself, because there's no rule, like kind of like like the equation that isn't at the top remains at the top. You know what I mean? Like they can be like all scrambled around when you switch the orders. So, but if you kind of draw the arrows, they do kind of do like the heavy work for you. Like it's just like going carefully, paying attention to what's happening there, and then you know the other thing that for like the y bounds, which tend to be easier, like once they are like the outer bounds, it's just like the maximum and smallest and largest value of y in the region, which is also happens to be here 0, 1. So I'll put 0, 1. And so that is how, for this particular problem, the two bounds the two orders would look like. Okay, now let's do another one. And okay, so same thing, but now just like again, let's set up the bounds. Bounds for of x and y, where R, or the region R, um, the region R is now like just a unit disk, let's say. So this is going to be like a useful example, because if we get time to talk a little bit about polar, I'll redo this one once we have polar coordinates, which I guess you have done in Calc 2 some polar coordinates, right? So I think, but I'll kind of like explain it again from scratch. So the units, like the unit disk is just the inside of the unit circle. So you have like the region R, just being all of this, right? So again, there are two ways to set it up. If you want to do like the vertical order, you draw the arrows like this. So if you do the order dy dx, what's happening here is that for the y bound, So for the Y bounds, like, the arrows go from the, like southern hemisphere to the northern hemisphere of the circle, right? So essentially what you have to do is take the equation of the circle and solve for Y in this case. And so when you do that, you say y squared equals 1 minus x squared. And so y equals plus or minus root of 1 minus x squared. So the plus minus is important here because that gives you the bottom and top bounds in the integration. So you get minus root of 1 minus x squared and plus or the root of 1 minus x squared. And then the x bounds are just like the minimum and maximum value of x on the units disk, and that's like between -1 and 1, right? Um, So again, like it's not that much harder than the previous one. It's just that it's kind of nice to compare later with the ones we switch to polar because if we had put like an actual function to work with this, then like at some point you have to evaluate these y bounds, and so you have to be working with square roots inside the integral, and that's kind of like a nuisance. So polar coordinates will kind of fix that issue where like the bounds will look a lot more simple. So. And then the order of the x, y is more or less the same idea. Okay. Okay, so the arrows look like this now, and so you essentially do the same, but now use the equation of the circles to solve for x instead of y. So when you take the circle as x squared as 1 minus y squared, and then take plus minus. So they go from like the western hemisphere to the eastern hemisphere of the circle. So this minus root of 1 minus y squared to root of 1 minus y squared. Okay. And similarly for the y bounds, like the minimum value is at the south pole of the circle, and then the maximum value of y is at the north pole. So the y bounds go from -1 to 1. Yeah.
Is there any reason why the arrows like the other do like this?
Oh, so the thing is, it's kind of like the convention is similar to, it's kind of like saying like when you write like a integral, like, like ordinary, when you write like an integral, usually a definite integral, like the lower bound is a smaller number. In fact, when you have something like, if you write something like the integral from 5 to 3, that kind of looks a bit odd. And the first thing that you do is kind of like flip the bounds and put like a minus sign in front of it, if you know what I mean. So yeah, in a sense, you could like change the order of the arrows, but the price would be put in minus signs, like if that makes sense. So it is like the convention is just kind of to write it in a way that's increasing in the variables, because that it really matches to what for like a single integral you would do when you put like the bounds like from like the smaller value to the higher value. Because again, like this is kind of like a it is can be written like that, but it does look a bit odd to put it there in that form. So it can be done, but kind of no, you know what I mean? Like you do want to avoid doing that because it just looks a bit odd. But of course, if you're consistent and you put it like this with a minus sign, then yes, it's fine. Like, you know what I'm saying, but it does look a bit weird. Any other one? Okay, now let's do the next one, which is interesting. because it does start showing you some of the differences sometimes between the orders of integration. So like right now, there's not much of a difference in the examples I have done so far. It is true that it's a bit more inconvenient to think of the equations as being in terms of given in terms of x, because usually you think of the equations more like for y equals like as y equals something. So there's some psychological difference there, but it's not like a major difference. But there are other problems where like, there are like practical advantages to using one order over the other. So let's just discuss this first. I'll do two more examples. I think I'll do two more examples of double like Cartesian coordinates. And before starting telling you a bit about polar coordinates. So now the same as before, but now the region R is the inside of the triangle with vertices, let's see, -1, 0, 0, 1. Okay, so let's draw this first. Another one, 0 is here. 0, 1 is here. And 1, 0 is here. Okay, so that is the region, the interior of this triangle. So again, there are two ways to do it. So if you do it vertically, let's think about what's happening here. So well, I don't know. Can anyone see what potentially what the issue? Well, not issue, but like there is something that we do need to take care of. If you think about this order vertically, but something new does happen.
The bound changes.
Right, exactly. So the point is like the exit, like where they exit does depend, right? Like sometimes they will exit through this side of the triangle and other times will exit through the other side. So the only way to deal with that is to just break it into two pieces, okay? And so once you divide, like kind of split the triangle in half, and then you do put like the corresponding bounds for each piece. So perfect. So let's just put like the equations here. So let's see, like the first one, I suppose this is like, and then you have to remember also how to find the equations of the lines, and you find the slope. Once you have the points for like the lines, right? So you have like want to find a line that goes through these 2 points, you have like that point, so you can find the slope, and then you can find the equation of the line. So what it would be something like x plus 1, this one, I think. And then the other one is negative x plus 1. Well, let's put it here. Right, because this one is increasing, the other is decreasing. Okay, so they all start all the arrows start at y equals 0. So let's just put that here. But say if you want the part that terminates at y equals x plus 1, which is the left side. So let's put here y equals x plus 1. Then that happens when x is between -1 and 0. So let me just write some more things to make this look a little bit better. So again, we're doing like the integration first with respect to y and then x. And so like the x bounds, when does this happen? When x is between -1 and 0. So let's put the 0 here. So x is between -1 and 0. Is that making sense? So that corresponds to half of the triangle, and then you just add the contribution from the other half. So you so the other half is when from y equals 0 to the other side, which is minus x plus y, right? And then and then the what like again, sorry, let me write like the f thing. So let me write f of x comma y dy dx. And for which values of x does this occur? It occurs when x is going from 0 to 1. So that would be the second half.
Wait, can you also express it as, one by using negative absolute value of x plus one?
Oh, right. So in this particular case, yes, like if you, right, that's like a good like observation. So in this case, yes, like you could use the absolute value, so you could write it as a single integral. From like I'll put it just like quickly from -1 to 1, from what 0, y equals 0 to y 1 minus absolute value of x, right?
Yeah.
Yeah, so good. That is true. Um, for this particular region, of course, now once you have again, like once you imagine like you're integrating this for a particular function, once you have absolute value of x, more likely than not, you will have to break it to integrate the absolute value. So you're kind of like postponing the breaking, like which is fine, but because it does look nicer with absolute value here, but it will like once you have like a concrete function, almost always like you would end up breaking it to like integrate the thing with that absolute value. If that makes sense. So it's kind of like better to kind of like absorb the damage at the beginning. I just like write it as two different pieces, because also like maybe like in a different problem this could have been like a line, but maybe then the other one is like a parabola. Like you could have changed or like something more like something different, where like it really cannot just be done with absolute value. But yeah, for this one, absolute value does work, but it in a sense it's kind of postponing the issue, if you know what I mean. Now the cool thing is that if like this starts showing you like a bit of the difference sometimes when you do different orders of integration. Oh, before I continue, sorry. Another thing that is also like a common question is, can you just say like that this two is twice one of the integrals, right? But because of some symmetry or things like that. But the problem is that you cannot really say that, like say like this sum is twice like the second term, because you don't know anything about the function f. So you don't know whether the function itself is like even or odd or anything like of that sort. So you cannot really replace, if you don't know anything about the function, you cannot really replace this with a single integral. Because if you remember from Calc 1, sometimes when the function was like, like even like the integral from -a to a is 2 times the integral from 0 to a, or something like that of the function. And that's all nice and good, but you do need to know something about the function. Like here, if I'm just telling you that the function is called f, you don't know, you cannot really assume anything about it. So it is better not to, sometimes kind of like making extra assumptions about like like more properties of the function than you were told will lead to problems because then you will end up writing something that is not, won't be correct for every single instance, if that makes sense. So just keep an eye on that as well. Because it's like a common like temptation, like, it's like easy to make that assumption. Okay, so then what's nice about this example is that if you if you reverse the order of integration, what will happen in the opposite order is that there's only one double integral that's needed. So that kind of gives you like the contrast that sometimes like for certain orders of integration, really you would like, you would need to do two versus just one in the opposite, in the reverse order. Okay, so let's think about why that is the case. So now we're integrating first with respect to x and then y. And so you have here the x bound. So what's happening with the x bounds? Like you follow now the green arrows and you see they all start on this side of the triangle and then they all exit through the other side of the triangle. So it's really from one side to the other, like the equations are like unambiguous. So here, if you solve for x, you get x equals y minus one. And if you solve here for x, you get what, x equals y minus y. So those are going to be the two bounds. And then the y bounds are just like the lowest value of y and the top value of y, which happens at this vertex. And it goes from 0 to 1. Is that okay? Is that making sense? Okay, so again, this example is just to show you that, yeah, there are situations where, um, you know, doing one is, yeah, both can be done like in principle, but like in one order of integration, you would spend kind of like, in a sense, twice the amount of time because there are two double integrals that you would need to do. Whereas in the opposite order, like there's only one double integral that's required. Okay. Okay, so now for the last example of Cartesian, before telling you a little bit about polar, here's an example where like literally one of the orders is basically impossible to do, whereas the other order like can be done very easily. So let's take this as the final example. And for this, I do need like a concrete function. So for this to kind of be shown explicitly, you do need to have like a concrete function to be thinking about. So I'll take the function to be sine of x over x, which may look odd at first, but there's nothing really wrong with that. Like also like when you do calc one integrals, like when you do like calc one integrals, you can also like write like integrands that are just like a number, right? Of course, like what you can put inside it here, it can be a function of x, but sometimes you do work with cases where like there's only a number inside. So by the same logic, sometimes like your function can just end up depending on one of the two variables. They could also just be a constant. So like, like when I write like a function of x and y, I just mean something that potentially depends on x and y, but it is still allowed to, like just depend on one of the variables or even be like constant. So just like as a heads up that there's nothing like intrinsically wrong with that. So if you take that function and you take the, like the region R to be the inside of the triangle with vertices 0, 0, let's see, 1, 0, and 1, 1. Okay, so what happens for the double integral of this function? So first, as always, let's draw the region. So you have we kind of had worked with this triangle or like a similar version last time. But now like what I'm changing is like a bit like the function. So now doing this. Okay. So if you do this like vertically, if you do this vertically, if I let's just to even make the numbers nicer, let's say like let's call the vertices pi 0, pi. So that would just make the bounds a bit nicer to integrate because it's like a triangle. It will be like a trigonometric function. So in this case, when you have like the double integral of sine of x over x, if you're integrating first with respect to y, and then x, so the y bounds, they go from y equals 0 to the equation of the hypotenuse. Like in this case, like hypotenuse is just y equals x. So that's what y equals 0, y equals x. Oh, let me write it in a different color. And then the x bounds goes from 0 to pi. This is what you end up getting. Is that okay? Is that making sense? Okay, and then you're integrating first with respect to y. There's nothing that really depends on y in this problem, right? Like everything is like a constant with respect to y. So it's kind of like integrating 3 dx or 3 dy. It's just 3 times a variable, right? So like here, like the first integration with respect to y just gives you sine of x over x times y. And then it gets evaluated at y equals 0, y equals x. And whatever you get there, you integrate with respect to x. From x equals 0 to x equals pi. And so what does that give you? So again, y equals 0, you don't have to worry about anything. And once you plug in y equals x, that x will cancel this x. You're just really integrating sine of x dx. From x equals 0 to x equals pi. Okay, and well, that's an easy integral, right? Like that's negative cosine of x equals 0, x equals pi, and that should give you like 2 or something like that. Okay, so that is what the that is what the double integral is supposed to give you. So you should just get 2. Okay, but what happens if you had tried to do this by reversing the order of integration? So if you reverse the order, okay, so it's still sine of x over x, but now we're going to put like the integral with respect to x first. We put the x dy. Okay, and so x, like if you do like the again like the the horizontal arrows. Now x starts at the hypotenuse, so you start at x equals y. That's the equation of the hypotenuse where they enter, and then you exit through x equals pi, And then y would go from 0 to pi. That okay? Is that making sense? But then the issue is that you have to integrate. Now, this is like an integration with respect to x first. So now you have to integrate sine of x over x with respect to x. And you could maybe think, oh, let's do like an integration by parts or something like that. There's nothing like useful that you will find there. There's really no good way to find like an antiderivative for sine of x over x in terms of like things, you have seen before. So you're basically stuck. You are not going to be able to find like the antiderivative for sine of x over x. Like that's the end of the story. I mean, you just cannot continue because like it's a crazy function to integrate. So just like literally you cannot do it. So you can't like no easy way to integrate this. Let's just put it like that. And that's it. Like, you could not have said what the answer is if you had used this order of integration. So the point of this example is that even though theoretic, like, that the answer has to be two, like the answer has to be two because it is the same number, right? It's just that there's no realistic way to find it in this other order of integration. So the point here is that there no there's simply no good way to to find this. So you cannot finish the problem here. You can't finish. In other words, so sometimes there will be certain functions where like one order is just like preferred over the other. Okay, so let me just write that down. So that is sometimes that is for certain functions. A particular order of integration, one of the orders of integrations can just be impossible. Of the orders of integration can be impossible. Basically impossible. Okay, does that make sense? So, like, of course, how do you know that? Like, that does require some, like, trial and error. Because again, like, maybe you could have tried, like, to do integration per parts or something of like that sort first, and then you kind of realize that you get stuck quickly. So it, like, usually what happens is like the function just looks a bit unusual. When you're trying to find like an antiderivative. And yeah, probably it's not a good idea to start with polar today. I'll do it on Monday, and that will be the last topic for the exam. But just to give you like an analogy, something like similar will happen. So that's like an example where like one order of integration is better than the other. Other things that can happen is that neither order works very well. So like for example, here's another example or here's an example where both orders are bad. Are pretty much useless. So if I wanted to do like an integral like this, I'm not going to give you the bounds, but like if I wanted to do like an integral like this, say dy dx or this is like a integral that appears multiple times in statistics and probability because that's essentially like the integral that represents like a Bell distribution. Like if you have seen like the basic like this bell-shaped curve like that appears everywhere. It's called like basically a rescaling of that is called like the normal distribution in statistics or like a version of that. There are variations of them. If you try to integrate this directly, you will fail. Like there's like basically no real good way to do this. But the key is to, if you look at the exponential, like the exponential like can be written like e to the minus x squared plus y squared, and x squared plus y squared is nice in polar coordinates, that's just r squared. So what I'll tell you next time is that, for example, if you wanted to do this integral, it is convenient to switch to polar because something magical will also happen once you switch to polar, which basically just to tell you quickly is when you switch to polar, and I'll explain this next time, these will become, it doesn't become just the r d theta. This is not what you get in polar, you get r the r d theta. And this extra factor of r would allow you to, do like a U-sub to integrate this very easily. So like there's like something miraculous like that happens there. And there's actually like a very cool video of 3 blue, 1 brown that explains like talks a little bit about the Gaussian distribution. I'll maybe ask you to watch it because it does like it is like that is kind of like the key distribution in statistics. So it's kind of like useful to know some stuff about it. So although I don't think it makes a lot of sense to start this today because we only have like 15 minutes. So let's Monday I'll tell you about polar coordinates, and that will be the last topic for the exam. So I already posted the solutions to the practice exams, but essentially you can do now 5 of the 6 problems. The only thing that you wouldn't know how to do is like the polar coordinates problems. So I'll see you on Monday.